In 1935, word went out across southern Ontario and British Columbia that a biological miracle had arrived. To combat root beetles destroying crops, landowners introduced the giant cane toad. The agricultural pests barely took a hit, but the toads seized the landscape, establishing one of the most aggressive invasions in North America. For decades, every attempt to curb them stalled against the same reality. A predator strikes, a rattlesnake, fisher, otter, or hawk, and within minutes lies lifeless in the brush. It seemed this amphibian was completely unassailable across the Canadian wilderness. Then, along a quiet lake in Manitoba, field biologists documented something unexpected. Tens of thousands of freshly metamorphosed toadlets were crawling onto the sun-baked shoreline. Waiting in the silt was an army of native thatched wood ants. The ants moved in instantly, biting, anchoring their jaws, and dismembering them on the spot. The critical mechanism, the lethal cardiotoxin that drops an apex predator like a lynx, has virtually zero effect on an insect. Indigenous Canadian frog species had adapted to this terrestrial dynamic over millennia. The invasive toad never stood a chance. Researchers began concentrating ant colonies along these critical exit corridors. What unfolded was far more devastating than initial models predicted. I'm Ambrose Wylde. Stay with me, because the mechanics of this ecological pressure are significantly stranger than the headlines suggested. Why does this chemical defense instantly stop a snapping turtle, pine marten, raccoon, or rattlesnake, while a native ant marches right through it? The physiological explanation is straightforward. The cardiotoxin evolved specifically to target vertebrate biology. A bullfrog, northern pike, and red fox all rely on the same fundamental architecture: a centralized heart, nervous system, and respiratory organs. The toad's poison targets those exact systems simultaneously, halting the machine with a single biochemical disruption. An ant does not operate on that framework. It possesses no multi-chambered heart, and whatever minor reaction the toxin triggers isn't enough to force the insect to release its grip. To an aggressive wood ant patrolling a lake bank, the most formidable chemical defense on the continent registers as nothing more than a foul taste. Are juvenile toadlets simply less toxic than adults? Not at all. The poison is present throughout every phase of the life cycle, from egg masses to emerging juveniles. Younger specimens contain smaller volumes, but the toxic payload is fully functional, yet the ants attack relentlessly. If the poison posed a legitimate threat to the colony, you would observe a rapid drop in attacks after the first few casualties, just as mammalian predators learn to avoid the species. That decline never happens. Day after day, the colony returns to repeat the process. The toad spent millions of years perfecting organic armor against vertebrate biology, only to walk directly into an opponent that lacks a spine entirely. When I mention researchers concentrated ant populations along the shoreline, you might picture heavy machinery, crates, and technicians in biohazard gear releasing millions of insects over a wetland. The reality was a tub of commercial canned fish. Field teams laid simple bait trails along the exposed silt where the young emerge and monitored the perimeter. Within hours, an otherwise quiet stretch of lakeside mud transformed into an active feeding zone. As juvenile toads scrambled out of the water, 98% were ambushed within their first few minutes on land. No exotic bioagents, just existing native pressure placed in the exact right spot. How did this invasive species gain such a foothold? Back in 1935, cane toads were delivered to agricultural districts as a living control agent. The blueprint was simple. Toads devour crop-damaging beetles, protect the harvest, and remain contained. The beetles were virtually unaffected. Left unchecked, toads exploited a land with no natural defense against them. Tracking historical distribution maps reveals the sheer scale of the spread. Through the mid-20th century, the invasion front advanced at 10 to 15 kilometers per year. By the early 2000s, across key lake systems, that frontier surged forward at 50 to 60 kilometers annually. How do you disrupt an invasive population that cannot be poisoned out, cannot be outbred, and is constantly gaining ground? You target the single operational window where the animal has no choice about where it stands. Immediately following metamorphosis, thousands of former tadpoles leave the aquatic environment in unison. Around a single marsh, the shoreline turns into a writhing carpet of life. Hundreds of tiny juveniles emerge simultaneously, soft-bodied, slow-moving, and no larger than a thumbnail. They are biologically incapable of retreating directly into the dry forest interior. A newly emerged toadlet loses moisture rapidly, trapping it along the narrow, humid strip of damp mud until its skin thickens. The shoreline acts as an inescapable physical bottleneck. Every single individual is funneled through the exact same strip of wet earth during daylight hours. When the target is small enough, brute force becomes secondary to sheer numbers. Native wood ants patrolling ashore hunt through numerical superiority. A single bite brings dozens of reinforcements within seconds. They swarm the toadlet, locking mandibles onto its limbs and anchoring it to the mud. The animal thrashes frantically, but that movement vibrates the soil, signaling even more ants. Shortly after, the movement stops entirely. The ants possess no potent neurotoxin and deploy no complex strategic maneuvers. Simply dozens of mechanical mandibles applying continuous pressure at the exact same time. Dot field data is stark. Over half of all ant attacks on emerging toadlets result in immediate mortality. For those that break free, roughly 88% perish within 24 hours, not from secondary predators, but from cumulative physical trauma and stress caused by the initial ambush. A single morning along a ribbon of mud can effectively erase an entire local generation. Why aren't Canada's indigenous amphibians, like leopard frogs, wood frogs, or American toads, being wiped out alongside them? Native species have coexisted with predatory ant colonies across Canadian wetlands for thousands of years. They evolved precise survival instincts, remaining motionless at critical moments, executing sudden leaps, and moving away fast. The invasive toad possesses none of these behaviors. It evolved in tropical environments where large terrestrial ant colonies do not patrol the waterline, so it never developed the necessary evolutionary instincts. Laboratory trials comparing maximum jump distance, acceleration, and stamina between the invasive species and 7 native Canadian frog species showed the invasive toad finishing dead last in every physical metric. Then comes daily timing. Most native frogs emerge under the cover of night, when wood ants are completely inactive. Invasive toadlets cannot wait for nightfall. In the dark, larger adult toads patrol the margins, and the threat of cannibalism forces the young to emerge in broad daylight, stepping directly into active hunting grounds. Why are invasive toads still expanding across watersheds? Because while pressure is intense, it is strictly localized. The outcome depends on environmental variables: recent rainfall, soil composition, whether the bank consists of sand, clay, or granite, and the proximity of ant mounds. On ideal shorelines, ants create an impenetrable barrier. On others, toads pass through unhindered. Furthermore, toadlets will scramble onto emergent vegetation, fallen logs, or floating debris to stay elevated above the mud. The microtopography of the ground itself plays a decisive role. Deep cracks in dried mud, small depressions, and heavy livestock footprints transform a smooth bank into a maze of obstacles. To a fragile juvenile the size of a fingernail, a cattle footprint represents a massive crater. It gets trapped inside, loses momentum, and the ants don't even need to give chase. A single cow walking along a bank in rural Ontario can inadvertently seal the fate of hundreds of emerging toads. When field biologists refer to ant predation, observations primarily highlight thatched wood ants from the genus Formica, abundant, territorial, and naturally adapted for foraging along wetland edges. But they only control the terrestrial exit zone. Below the waterline, aquatic pressure begins earlier. Giant water bugs, dragonfly nymphs, and diving beetles actively hunt toad tadpoles. Above the surface,
Shore beetles and predatory bugs feed on egg masses.
None of these species work together. They simply happen to exploit different stages of the same life cycle. Why not import larger, more aggressive ant species from overseas to finish the job? Introducing non-native species like European fire ants into Canadian ecosystems has already proven to be an environmental disaster. They coordinate via chemical trails, swarm rapidly, and deliver painful stings that disrupt local wildlife and humans alike. That isn't targeted pressure. It is compounding an existing problem with an even worse ecological threat. Working with native wood ants represents the opposite philosophy. The predator is already established. You are simply steering existing biological pressure toward a specific one-week window and narrow strip of terrain where the invader is totally exposed. A country that has experienced the fallout of well-intentioned biological interventions in the past ought to recognize the importance of this distinction. Controlling an invasive species almost never means complete eradication. It means stopping exponential population growth, relieving pressure on native wildlife, and forcing overall numbers down to manageable levels. Expecting complete elimination of a species already established across thousands of square kilometers is unrealistic. No one involved claims we can completely remove this animal from the Canadian landscape. The goal is to strip away its momentum. Yet, a profound shift occurred here. The cane toad evolved an absolute chemical defense that rendered it untouchable to vertebrate predators, a biological shield that continues to function perfectly today. Rattlesnakes still succumb to the toxin, fishers still die, snapping turtles still perish. But that defense never accounted for being dismantled by a creature weighing less than a fraction of a gram on a muddy shoreline before it reached its second week of life. Its biological armor was built for an entirely different kind of battle. Before examining how an entire regional food web collapses under an invasive species, we need to look at what actually happens inside a native predator when it encounters a giant cane toad. The mechanical reality of this poisoning is relentless and instantaneous. The toad does not bite, sting, or project defense through the air. The weapon sits inside massive parotid glands, located directly behind its eyes, ready to deploy the moment a predator applies physical pressure to its body. When a fisher, fox snake, or river otter grabs a toad, those specialized glands compress like squeezed sponges, discharging a milky secretion known as bufotoxin directly into the attacker's mouth, eyes, and throat lining. The biochemical compounds within that fluid do not require an open wound to enter the circulatory system. They pass through delicate mucous membranes in seconds, entering the bloodstream and moving straight toward the heart. Within 90 seconds of contact, the cardiotoxin locks onto the sodium-potassium pumps within the predator's cardiac muscle cells. These biochemical pumps maintain the precise electrical voltage required for a vertebrate heart to contract and relax. The toxin binds permanently to those molecular gates, disabling them entirely. The immediate consequence is a catastrophic spike in calcium levels inside muscle tissue, forcing the heart into violent contractions before locking it into absolute cardiac arrest. For a mature rattlesnake or red-tailed hawk, there is no incubation period, no gradual onset of illness, and zero opportunity to build biological immunity. The animal experiences severe disorientation within 2 minutes, loses muscle control, collapses into violent convulsions on the riverbank, and perishes before the toad even makes it back to the safety of the reeds. This precise interaction explains why the arrival of the cane toad across Canadian watersheds triggered an ecological disaster. Traditional invasive species typically displace native wildlife through competition for food, nesting sites, or clean water. The cane toad introduced a different threat vector. It transformed the act of hunting into a fatal trap for every major apex predator in the region. Consider the impact on the massasauga rattlesnake, Ontario's only native venomous snake, and a critical controller of small mammal populations. In sectors where the toad frontier advanced, field researchers documented regional massasauga mortality rates exceeding 70% within 18 months. Driven by millions of years of predatory instinct to strike at prey, the snakes had no evolutionary reason to avoid the slow-moving amphibians crawling across the forest floor. A single strike resulted in the death of both prey and predator. The exact same destructive dynamic played out across populations of fishers, pine martens, and river otters along northern river systems. Apex predators that had spent generations regulating local aquatic and terrestrial balance were suddenly being erased from the ecosystem, not by habitat loss or overhunting, but by a fatal biochemical mismatch. As apex predator numbers collapsed across affected Canadian provinces, the loss rippled through every level of the local food web. With fishers and rattlesnakes disappearing from wetland margins, secondary consumer populations began to surge out of control. Small rodent populations exploded in agricultural sectors, leading to increased crop damage and higher transmission rates of tick-borne pathogens. Native frog species, already struggling against habitat fragmentation and water pollution, found themselves double-teamed. On one side, giant invasive toads were outcompeting them for breeding sites and devouring their egg masses. On the other side, an unchecked population of mid-level predators, freed from apex control, was consuming native amphibians at unprecedented rates. What made this dynamic uniquely dangerous was its total asymmetry. The cane toad was effectively immunizing itself against the apex predators of North America, while simultaneously devouring the foundational layers of the native food chain. For nearly half a century, wildlife biologists, provincial ministry officials, and conservation groups tried every traditional management technique in the book to stem the tide. They organized mass manual culls, deployed mechanical traps along wetlands, constructed barrier fencing around sensitive breeding grounds, and even experimented with biological scent deterrents. Millions of tax dollars were poured into regional containment programs, from the Great Lakes Basin to western agricultural valleys. Every single effort failed. Manual removal teams could clear tens of thousands of adult toads from a park system over a single weekend, only for millions of newly metamorphosed toadlets to emerge from surrounding marshes 2 weeks later. The invasive amphibians' reproductive capacity, with a single female capable of laying up to 30,000 eggs in a single clutch, rendered conventional human intervention utterly meaningless. The species was moving faster, expanding further, and consuming more territory with every passing season, leaving behind a trail of silent wetlands and broken food webs. By the late 1990s, the official consensus among wildlife agencies was bleak. The giant cane toad was considered an irreversible ecological reality in North America, an unstoppable force that would permanently alter the biological character of Canadian wilderness areas forever. Then came the observation along the shores of that Manitoba lake that changed the direction of invasion biology. When researchers realized that native thatched wood ants were casually dismantling juvenile toads without suffering ill effects from the deadly poison, it forced a complete reevaluation of how we fight invasive species. The answer was not going to come from human technology, chemical sprays, or artificial barriers. It was hidden right beneath our feet, inside the complex subterranean colonies of an insect that had been quietly managing wetland margins for thousands of years. To truly appreciate how a native insect manages to neutralize a toxic biological invader, we have to look past the surface drama of the lake bank and examine the incredible mechanics of ant supercolonies. Along the damp shorelines of Canadian shield lakes and southern river systems, thatched wood ants operate as a single, distributed organism. A single mature colony of Formica can contain hundreds of thousands of individual workers, all connected through intricate chemical communication channels and working in perfect organizational synchronization. Unlike mammalian predators that rely on individual hunting tactics, wood ants hunt through continuous, highly organized territorial saturation. They do not possess large eyes or advanced spatial tracking abilities. Instead, they process their immediate environment through a constant stream of chemical signals and tactile inputs. Every second, thousands of foragers fan out across the forest floor and muddy shorelines, establishing dense networks of pheromone trails that link the central nest directly to high-density food sources. When a foraging wood ant encounters a newly emerged cane toadlet on the damp silt, the interaction is governed entirely by instinctive behavioral algorithms. The ant does not pause to evaluate the size, shape, or potential toxicity of the animal blocking its path. To a wood ant, any soft-bodied creature moving through its core foraging zone is either a potential food resource or an immediate threat to the territory. The ant lunges forward, driving its sharp mandibles into the toadlet's delicate skin. As it bites, it releases an alarm pheromone, a potent chemical signal that diffuses through the air and soil within seconds. For nearby nestmates patrolling the same section of bank, that chemical scent acts as an immediate beacon. Within 30 seconds, what started as a single, isolated bite escalates into an organized tactical response as dozens of ants swarm toward the chemical signal, converging on the struggling juvenile from every angle. Here is where physical dynamics of scale completely turn the tables on the invader. When a mature predator like an otter or a snake bites an adult cane toad, it applies immense pressure to the parotoid glands, triggering a massive, lethal discharge of poison into its mouth. But a juvenile toadlet, emerging from the water at the size of a human thumbnail, simply cannot deploy that chemical defense effectively against a swarm of microscopic attackers. The individual bites from the wood ants are localized and precise. Rather than squeezing toxic glands and releasing a flood of poison, the ants grab hold of the toadlet's tiny limbs, eyes, and belly, pinning the soft-bodied amphibian directly against the mud. The toadlet's natural instinct is to thrash wildly to break free, but that kinetic movement only sends shock waves through the damp substrate, drawing even more ants to the location. As the ants anchor the juvenile in place, they deploy their own specialized offensive weapon, concentrated formic acid. Spraying this caustic compound directly into the microtears made by their mandibles, the ants induce rapid physical shock and total systemic collapse in the toadlet long before any bufotoxin can affect them. The biochemical immunity of the ant itself is a marvel of evolutionary design. The cardiotoxin contained within the toad's body was naturally selected over millions of years to disrupt the specific sodium-potassium ion channels found in vertebrate cardiac tissue. Invertebrates, like wood ants, rely on an entirely different physiological architecture. They lack a closed circulatory system and a centralized, multi-chambered heart driven by complex electrical signals. Instead, their hemolymph flows freely through open body cavities, and their muscular contractions are governed by decentralized nerve clusters dotting them. The complex chemical molecules that instantly halt the heart of a snapping turtle or a red fox simply have no molecular target inside an ant's body. The toxin registers as nothing more than a bitter fluid. Even if an ant ingests small quantities of the poison while dismembering the juvenile, its specialized digestive tract breaks down the organic compounds without allowing them to cross into its vital systems. This fundamental biochemical mismatch creates a fascinating ecological reversal along the Canadian shoreline. An invasive species that spent millions of years perfecting an impenetrable shield against the most dangerous vertebrate predators on the planet walked straight into a habitat where its master weapon is completely useless. The very chemical defense that allowed the giant cane toad to conquer thousands of square kilometers of Canadian wilderness loses all power against a common native insect weighing less than 5 milligrams. What human managers failed to accomplish with decades of expensive culling programs, toxic sprays, and mechanical barriers, the humble wood ant achieves through simple, relentless arithmetic on a sunlit patch of mud. When you step back and look at what field biologists are actually doing along these targeted Canadian shorelines, the true genius of the strategy becomes clear. This is not about introducing some hyper-aggressive alien species or unleashing an unpredictable biological experiment upon the landscape. We are talking about leveraging a native predator that has been part of the Canadian wilderness since the last glacial retreat. The wood ants belong here. Their populations are naturally regulated by local winters, native birds, and shifting forest dynamics. By simply placing inexpensive, biodegradable bait trails along known emergence corridors during that critical one-week window after metamorphosis, conservation teams are not altering the environment. They are simply guiding existing ecological pressure toward a precise physical bottleneck. It is a surgical strike deployed against an invasive giant at the exact moment its armor is thinnest. The broader lesson here extends far beyond the margins of a single Manitoba lake or Ontario wetland. For nearly a century, our approach to invasive species management across Canada was defined by brute force and heavy intervention. When an aggressive invader established a foothold in our forests or river systems, the default response was to throw millions of dollars at chemical treatments, physical barriers, or massive culling campaigns. We treated biological invasions as military battles to be won through sheer human willpower and technology. But ecosystems do not respond to brute force. They respond to evolutionary pressure, physiological constraints, and functional balances. The cane toad's conquest of North American habitats seemed unstoppable only because we were measuring its strength against vertebrate biology, the exact arena. Yet in the end, its relentless expansion was halted, not by a grand technological breakthrough, but by a microscopic flaw in its evolutionary blueprint, exploited on a quiet strip of muddy shoreline by a native insect weighing less than a single grain of rice. If you find these hidden ecological turns as fascinating as I do, make sure to stick around. There is a whole world of seemingly invincible invaders out there that met their match in the most absurd, unexpected ways, and we are going to explore every single one of them. I'm Ambrose Wylde. Thanks for watching, and I'll see you on the next journey.